Hello and welcome back to the Cutting Edge stage at CogX 2021. I'm your MC, Jess Wade, a research fellow at Imperial College London. Please remember to share your thoughts and ideas on social media using the hashtag CogX2021. Now we're sidestepping into another area of cutting edge technology, the power of probabilistic programming, which could help to accelerate programming culture. We're incredibly lucky to be joined to not only see Gemma Milne return to our virtual stage, but the AI pioneer Stuart Russell, Professor of Electrical Engineering and Computer Sciences at UC Berkeley and adjunct Professor of Neurological Surgery at UC San Francisco. Whilst we're always thrilled to have Professor Russell joining us, on Saturday, he was awarded an OBE in the Queen's Birthday Honours. So having him today is extra special. Gemma, please help me understand what probabilistic programming is and also get excited about it. Over to you.
Thank you very much. I'm going to share my slides. We're going to have a very traditional presentation. And okay. So let's start with a quote from Francois Charles, who's a very famous deep learning researcher. And at the end of his book, he says, many more applications are completely out of reach for current deep learning techniques, even given vast amounts of human annotated data. And I think this is a sentiment that many deep learning groups are probably whispering to themselves, but not daring to say out loud. The main directions in which I see promise are models closer to general purpose computer programs. So that's Francois Charles. Meanwhile, there is already a discipline within computer science that learns models that are general purpose computer programs, and that's called probabilistic programming, which began with a paper in 1997 and has been expanding ever since. So the basic idea of probabilistic programming is to take two incredibly powerful mathematical theories. One is probability theory, which allows us to handle uncertain information, to learn from data and so on. And the other is the Turing machine, the universal expressive power that computers, programming languages, and first-order logic give us. So you take those two things together and you get something that's extremely expressive and extremely useful for learning. And to give you an idea of why expressive power matters, if we take something like the rules of Go, if we want to write those down in a programming language or in first-order logic, that's about a page, about as much as it would take in English. If you want to write it down in a circuit language, and neural networks are circuits, it would be about 1 million pages, because the circuit language simply lacks the ability to express the generalizations, the generality of the rules of Go, the fact that they apply to every square of the board, the fact that they apply at every step during the game. Those things can't be expressed directly. So with these languages, because they are Turing equivalent, that means that we can represent any computable probability model. So anything that you can write down in any formal language of any kind can be written concisely in one of these languages. We can also have general purpose inference and learning algorithms. So inference and learning in these languages are really the same thing. And we can have one algorithm that will work for any model, for any data, and for any query. So really, you don't have to write any code. You don't have to do all the math. You simply write down what you know about the problem, you supply data, and off you go. Another big advantage is that whereas in neural networks, we supply data, and maybe we get to fiddle with the architecture of the neural network a bit, we can't easily supply prior knowledge about which we have vast quantities. And also, you can't get cumulative learning to happen in a natural way in neural networks, but in probabilistic programming, it can. So this is the standard description of what happens in machine learning today. The data comes in, you do some learning, and out comes some knowledge in the form of a trained network. So what we would like to do would be to supply knowledge to that process as well. So, for example, when a physicist is interpreting data from a collider, the physicist actually knows some physics. And if you didn't know the physics, you'd have no idea what the data meant. We also want this to be cumulative. So whatever is learned is then added back into the knowledge that can be used for the next phase of learning. And so this is really how human beings and human civilization works. And this can be done within probabilistic programming. So the field is really exploding. It was very quiet until around 2008. And now it's growing exponentially. We're up to over 2,500 papers per year being published. I'll talk about one application, which is to the Comprehensive Nuclear Test Ban Treaty. So this treaty bans nuclear tests, of which we've had more than 2,000. And the fallout from those tests has killed at least 100,000 people. Some estimates go up to 2 million. And the tests leave things like this, big hole in the ground in Nevada. And here's how it works, right? So we have a global network of detection stations, mostly seismic stations, all around the world, called the International Monitoring System, or the IMS. And from these detection stations, we collect the raw waveform data. And this is the seismic data, those kinds of squiggles that you see when there's an earthquake. And then from that, we have to produce a daily bulletin. These are all the events, the large energy release events that happen anywhere in the world. And so the evidence is the waveforms from the seismic stations. The query is what happened today. And the model, the part that we write in the probabilistic program, basically contains the elementary geophysics of where we expect natural events to occur, how seismic signals are transmitted through the body of the Earth, how the detectors work, and how much noise there is. And this is the model. So this is a probabilistic program written in a language called BLOG, which stands for Bayesian logic. I'm not going to go through it line by line. If you were a geophysicist, I could sit you down and in 5 minutes you would understand exactly what this is saying, because this is really geophysics 101, the sort of the simple elementary theory of how seismic signals work in the world. So with that, and then historical data from the network, we're able to produce a system that is extremely good at detecting seismic events anywhere in the world. And this shows the detection that happened in real time for the North Korean nuclear explosion in 2013. And the system is about 3 times more accurate and sensitive than the previous version, which the geophysicists took about 100 years to develop. It took us about half an hour plus a lot of work to make it run fast to develop the real system. Here's another simple example. I won't go through the code, but this is just to show this is the state-of-the-art model for tracking objects in real time in video. And there it is in about 4 lines. And because it's very simple, and because we don't have to do the math and we don't have to write the code for the inference algorithms, we can improve this model very simply. So if we want to improve the continuity, we can just change the model in that way. And then we actually get real-time computer vision tracking of moving objects that works better than the standard state-of-the-art in the OpenCV package. So to summarize, I actually believe that probabilistic programming gives us a way forward. I think deep learning may be running into a brick wall because probabilistic programs allow this cumulative knowledge-guided learning process, which means that you don't need vast quantities of data. You actually get better at learning as time goes by. It has very great expressive power, so we can learn very complicated models very quickly from small amounts of data. And it's built on thousands of years of mathematical research. And that means that we have all kinds of advantages in terms of understanding what's actually going on. Now, some people really like deep learning, and that's fine. And there are languages like Edward and Pyro coming out of Facebook and Google and Microsoft and so on that combine PPLs with deep learning, and that's a very promising combination. And for those of you who worry about computation speed, particularly if you've used some of the widely available BaseNet packages such as bugs, two things. One is that these languages are much, much more expressive than BaseNet packages. And two, they come with compilers that give you code that runs about 1,000 times faster than most of the commonly used BaseNet packages. So if you're interested, you can go to probabilisticprogramming.org, or you can just type probabilistic programming into Google Scholar and find those thousands of references. And that's it.
So thank you very much for that. So for anyone who's watching, I want to take your questions and make sure we can put them to Stuart. So pop them straight in the chat right now. I've got a couple of questions of my own, but I will weave your questions in as we go. So please do type away at any point. Stuart, I wonder if you could kind of give us a bit of context as to why we're talking about this right now. You said that obviously there's been this, acceleration or boom, shall we say, of papers to do with probabilistic programming. But what is it that's fueling why it's interesting right now in 2021? Is it this, as you say, the barrier, the kind of brick wall that deep learning is coming up against, and we're now looking for something different? Is it tech? What is it that's fueling this new interest?
So I've been interested in it for almost 30 years. I've been.
Well, you're ahead of the curve then. Ahead of the curve.
Because it's in some way a natural extension of ideas, as I say, that date back hundreds of years of how to use probability. And I think one of the reasons that people are thinking about maybe switching is that in deep learning, there's starting to be some cracks showing. There's a paper from MIT, you can look it up under overinterpretation from Dave Gifford's lab. And they showed that the computer vision algorithms that are supposedly very, very good at recognizing objects in images are actually, in many cases, not looking at the objects at all. So the algorithms have learned that you can recognize what kind of dog it is by looking at the carpet that it's sitting on or the grass that it's sitting on, because that regularity shows up in the data set, even though it doesn't show up in the real world. You can find out that something is a parachute not by looking at the parachute at all, but just looking at how much sky there is in the image. In other cases, you can classify an object as a fighter plane by looking at a single pixel and seeing that it's gray, and then announcing that this is a fighter plane, right? So clearly, it's not the algorithm's fault. The algorithms are told, here, take this 1,000 by 1,000 array of numbers and predict the label that people are going to stick on it. And it has no idea that there's supposed to be an object, and the object's supposed to be in the middle, right? I mean, it just learns whatever regularities it can learn. And the fact is that often it's learning completely the wrong regularity, and it's not really generalizing, and it's not recognizing the object in the way we think that it might be. Another big paper came out of Google on what they call underspecification, and they found that for dozens of real-world deployments of deep learning systems, the actual performance was far lower than they had been led to expect by the results, the standard train test accuracy results that they got in the lab. And that's, again, because once you're out in the real world, you actually have a different distribution of images, backgrounds, cameras, and so on, and the systems are just performing quite poorly when they get into real data. So there's a number of things happening that are making people wonder whether deep learning is in fact the way forward. And as Francois Charles said, you can't fix the problem by just having billions of pictures of dogs instead of millions of pictures of dogs.
Let's build. You mentioned Google there, and you mentioned, of course, in your talk as well, the various groups that are happening in corporate settings, Google, Facebook, Microsoft, really investing quite a lot into this area. Could you tell us a little bit about perhaps what each of them are doing, what differentiates, what are the different languages that are kind of on offer, and also just a little bit of context as the difference between what's happening in the academy versus what's happening in these corporate settings.
So I think in the corporate setting, they're really interested in scaling up, and often they're happy to have slight restrictions on the expressive power of the language so that they can guarantee that the inference is going to run fast. So Microsoft, for example, has a language called Infer.net, and then there are other various probabilistic programming languages for specific tasks. I think one is called Tabular, that's sort of probabilistic programming with spreadsheets. Infer.net is used for TrueSkill, for example, which is the model that estimates how good a game player is. Microsoft has its game platform with hundreds of millions of players, and every day the TrueSkill model is taking all the results of all of those games and giving people their numerical rating score on how good they are in that game. And that's a probabilistic program. Roughly speaking, the idea is that that you have an intrinsic ability at this game, but sometimes you have an off day. Sometimes you're unlucky in a match. Sometimes you come up against someone who's lucky in their match, and so it's a probabilistic inference process. And gradually, as you see the results of various games, you can start to get a better handle on how good a given player is, and that's what TrueSkill does. So they are interested in scaling that up because it's giving hundreds of millions of ratings every day, and it's using data from every single player to estimate those ratings.
I'm going to go to a question actually from the audience because we're already getting quite a few in, and I want to make sure we get through these and I don't get caught up in my own ones. So let's just go to the first one from Raphael. He's asking what your take is on probabilistic programming and quantum computing. Obviously, I'm assuming seeing the same sort of ideas there around using probability and these kind of methods to enhance the way we do computing.
Yeah, so I just had a long discussion last week with a quantum computing person, and I see several different directions to go. One is obviously that quantum computing could speed up the inference process, and mostly in probabilistic programming we use something called MCMC, Markov chain Monte Carlo, which is a randomized algorithm that generates samples of possible worlds and then estimates probabilities from that. So there's interest in quantum versions of MCMC algorithms, and that would be relatively straightforward because, in fact, the MCMC approach was developed by physicists in the 50s precisely for simulating physical systems, and quantum computing is a fairly natural fit for that. Another interesting direction is actually to have a language that represents complex quantum systems. So probabilistic programming is about probabilities. In quantum computing, there isn't just probabilities. There's actually the phase of the wave function. So it would be a sort of probabilistic phase programming language, if you like, that would be a natural fit for quantum hardware. And so that's something that's interesting to explore.
Amazing. There's so many coming through from the audience, so I'm gonna go just straight into these now because I want to make sure I get to all your questions as much as I can, guys. So we've got a question from Eugene Babaskin. Why are you using probabilistic programming and not taking integrals analytically?
Well, so there's no contradiction between probabilistic programming and analytical computation. So I said that we use MCMC in general, and that's because that is completely general and it works for any program. But wherever you can do an analytical integral, you can the inference engine can have a library of those, and whenever it's possible to do them, that's more efficient. But you can't do that in general because many of the integrals would be infinite dimensional and intractable to do exactly.
Amazing. Eugene, you're asking so many questions. Thank you. I'm going to come back to you after I've got to other people so that I don't keep biasing your questions. This one from Maria. In which sectors do you see that probabilistic programming will be available in the future?
Well, so it's completely general. So everything. I mean,
or maybe which ones you're more excited about, perhaps?
Which ones? So I think I'm actually really excited about its use for natural language understanding. And basically, the idea there is that there happens to be a real world. It's not often mentioned, but there is one. And language is usually about that real world, and it provides, so the text of language we think of as evidence, and then you're trying to infer what's being said about the real world and what might be true or false about the real world. And you can write that very naturally in a probabilistic programming language. And we actually showed that in a completely unsupervised way, so with about an 8-line probabilistic program that basically says there's a world, there are things in it, things are related to each other in various ways, and then you can express those facts by speaking. And then you can provide some raw text in a language that the system has never seen before, with no labels, so completely unsupervised. And the system learns the language, it learns what the words mean, and it's able to then answer questions about what's being described in the text.
Amazing.
Entirely by itself. So I think this is really exciting way of thinking about natural language, but trying to get the natural language community, trying to tear them away from their transformer models and other deep network models is really hard these days. I think everyone has blinkers on in terms of their thinking.
Well, let me then sneak in one of my questions then. Apologies to the audience, the joys of being a moderator. What are the challenges to adoption? You said you've been interested in this for quite some time, but obviously there is a bit more interest nowadays. What needs to happen in order to really accelerate the adoption in this, I guess, the shift of programming culture that was alluded to in the description of this talk?
So I think there's I would say a mental block in the machine learning community where people simply believe that any human provided information is illegitimate. So if we have to provide knowledge in the form of the probabilistic program, then that's sort of wrong. Now they're quite happy to spend months and months and months diddling with the structure of a network, or trying, putting in convolutions and this, that, and the other to try and get their application to work, but they don't think of that as providing knowledge, so that's okay. But this is obviously a bonkers attitude, because when people learn, we are not always newborn children. When I'm learning from data coming from a particle accelerator, I'm using what I know about physics and I'm adding to what I know about physics. And we should have our machines operate the same way. I think also at the moment, to use the technology effectively, I think you probably do have to understand probability theory, at least to a decent undergraduate level. And that's not so widespread. I would also say that there just hasn't been the level of engineering effort that has gone into languages like TensorFlow, and that's on us to make that effort, do all the engineering, and make it available to people. So there are lots and lots of languages that are available, but very few of them are well supported, have good manuals, have a large enough community of programmers. But I think there's right now the prospect that that could change fairly quickly. As we see more of these large applications come online, people will want to know, well, how on earth did you do that? And we'll say, well, you just have to learn a little bit.
Need stats 101. Speaking of which, then we've got a nice question from David Wood. He's asking, how do the probabilities feature in probabilistic programming? Don't deep learning networks already have probabilities? For example, the probability that a particular image is a 7 rather than a 1.
Great question. So the probabilities are in the probabilistic program. So what I showed you on the screen is the sort of the skeleton of the probabilistic program. But each of those, each line is a dependency statement. It says, how does one set of random variables depend on other sets of random variables? That dependency is then quantified using a conditional probability distribution. And those conditional probability distributions can be learned from data, whether you have labeled data for those particular random variables or not. It doesn't matter, because we can learn even with unlabeled information, and missing data and so on doesn't make any difference. And the cool thing is there are probabilities all the way through. So every step in this multi-step computation, every step involves conditional probability. So we can understand why the system reaches a given conclusion. We can generate explanations by tracing back the influence of all the different factors on the probability that comes out. And the probability calculations are such that the probabilities are always well calibrated with respect to the data, which is not always the case with neural networks. So neural networks do have, if you do cross-entropy training, then they can associate probabilities with individual outputs. But as soon as you go to outputs in more than one dimension, so for example, you're saying that this is probably a dog and it's probably weighs more than 50 pounds, expressing the joint probabilities over complex outputs is not something that's easy to make it happen in neural networks. So the other interesting thing is that for a feed-forward neural network, so now I'm going to get a little bit technical.
That's okay.
For a feed-forward neural network, the computation of the output given the input is linear time, right? So the amount of computation done is linear in the size of the network. And that sounds great, right? That sounds, well, it's really fast. But of course, what that means is that if the calculation you're doing is intrinsically a complex one, so if you're trying to make a decision that is intrinsically, cubic or even exponential, that means that you have to have a network that is cubic or exponential in size, right? So it has to have a vast number of parameters. And so you don't gain anything, because now it's linear in an exponentially large network, which really means it's exponential time. And it means that you require an exponential amount of training data to train that exponential number of parameters. And so I think this is one of the reasons why I don't expect that deep learning systems can break through the various barriers that they're running into, just for these fundamental points about the trade-off between computation time and sample complexity. So sample complexity meaning how much data do you need to learn a given thing, and really that's the currency that matters, because the universe only has a finite amount of data, and you can't just keep scaling up how many examples you need to learn each new thing.
So I'm going to bring in the question next then from Ian, which you have touched on quite a bit and I've made the case for, but let's see if we can go a step further. Ian says, surely back propagation based on quality data sets is still the ideal. The system is being delegated something that is time consuming for humans. If you have a data set, is this still preferable?
So that's an interesting question. And no, not at all. Right.
I thought you'd say that.
Why is that? Well, because data is not all we have. We have knowledge. And so we should use it. And the knowledge could be something that is provided directly by humans. Or it could be something that's, for example, extracted from text. So a lot of the knowledge we have, we learn from books, but then we have it, and then we can use it to learn new things from very small numbers of examples. If you look at human children and their picture books, that most children learn what a giraffe is from a picture book. They might not have the luxury of a zoo with a giraffe in. And interestingly, those picture books only have one picture of a giraffe. They don't have 40 million pages of giraffe pictures. And so how on earth do human children learn from only one example if they don't have the 40 million? Why is that? Well, it's because they bring something to the learning problem in the form of knowledge that they've acquired from their life of living in the real world. And so so I think we have to get people to see that learning is not taking a tabula rasa system and shoving data into it to learn some particular predicate. It's actually this cumulative process that ends up being much more data efficient than the tabula rasa process.
There's a nice question here from Raphael that I'm gonna bring to you next. Beyond learning equals labeling, there's increased talk in the AI community nowadays about the need for causality and embodied cognition. Is there any work happening to apply probabilistic programming to these spaces?
Sure. Yeah. So causality is fairly natural. I mean, Yuda Pearl's work on causal networks emerged from his work on Bayesian networks, and so it's relatively straightforward to apply the same ideas in probabilistic programming systems. So one way of thinking about probabilistic programming languages is that you start from Bayes nets, which have a very natural decomposition of probability distributions into products of conditional probabilities. So that idea is retained in probabilistic programming, but we're combining it with the expressive power of programming languages or of first-order logic, so that you can write down extremely complicated models in a very concise and natural way. So causality is a very natural fit for probabilistic programming languages. And I wouldn't worry too much about that in this context. I understand that people in deep learning are worried about it because they're not sure how to get causal modeling to happen correctly in neural nets. But I suspect that actually progress is occurring in that direction as well.
Another question based on where probabilistic programming can be pointed at, shall we say. Question from Ryan. What are the implications of this with autonomous vehicles?
So that's a great question. So as I see what's happening in autonomous vehicles, there were some groups who began with the idea that we could get the autonomous vehicle to work with end-to-end deep learning. And I sat down with Uber at the beginning of their program to develop an autonomous vehicle, and they were insistent on doing end-to-end deep learning. And I said, you're just going to kill people, and they did. What Waymo is doing is much more, should we say, like good old-fashioned AI. There's deep learning at the perceptual end, so detecting and classifying different kinds of entities on the road, whether they're cars or trucks or bicycles or sheep or plastic bags or whatever. But the decision making is not done using deep learning. It's done much more in the way that a chess program works, meaning that it actually projects into the future its possible actions and the possible actions of the other entities on the road, and then chooses the course of action that's most likely to lead to the best outcome. And so that's, again, this is a very natural fit for probabilistic programming, because you do want to deal with the uncertainty in what's happening. So when you're dealing with another vehicle on the road, and let's say they're in front of you, they're going quite slowly, and they have their their left turn signal on, and they've had it on for the last 5 minutes, right? So you're trying to figure out what on earth is going on. There's going to be uncertainty about the intent of the other drivers, and uncertainty in your ability to predict what they're going to do next. And so all of these things fit naturally in probabilistic programming. I would say, again, coming back to the question of engineering, the people in probabilistic programming haven't really worked on the engineering of decision making. So we've been focused almost entirely on questions of learning from data and prediction, but not the decision making capabilities. We did, just for fun, we built a system that plays blind Monopoly. So this playing Monopoly when you don't know where your opponents are and what properties they own. And it's kind of fun. It actually ends up playing pretty well. And it was another cool demonstration, because we could take the rules of Monopoly and express them very naturally in the probabilistic program. And then, it would collect evidence. Every so often it would have to pay rent, and then it would try and figure out why it was paying rent and who owned the property and whether it was going to be able to complete a set and so on, all based on these very partial clues coming in.
I'm gonna, about 4 minutes left, so I'm gonna ask you one of my final question, and we'll see if we've got time to squeeze in another if we do after that. But as somebody who researches hype and wrote a book on the problems of hype in science and technology, I wonder if you could tell me what the sort of state of hype is in probabilistic computing, probabilistic programming. Sorry, is there too much of it? Is there not enough? What are the limits? Obviously, this session is all about why it's the next frontier and why it's amazing, and you've made a really good case for that. But I'm asking you as a journalist and a researcher, what are the limits here? Where's the hype?
So I would say the two big obstacles, one I've already mentioned, which is the engineering. The other one is that inference is difficult. The computational cost of inference is difficult to control. And I think this is an area where we have to do a lot more work. And I think, some people are showing that actually deep learning can turn out to be useful for inference. So in MCMC inference, you can use anything you like to basically generate the next sample. And if you learn to be good at generating the next sample, then inference can go much faster. And some people, for example, Frank Wood, have shown that by using deep learning to learn to propose the next sample, you can get enormous speed ups in inference. So I think this is a very promising direction. I think also we have to put a bit more attention on what we call synthesis by learning. So producing the structural skeleton of the probabilistic programming by a process of learning, so that it's able to invent new functions, new predicates, new relations. And there's some preliminary work on doing this, but again, I would say it's not very beefy. So we need to put much more engineering effort into that.
More important that we hype it up and get more people excited so that we can solve those problems that you're talking about, right?
Maybe it doesn't. I mean, it doesn't require millions of people, but it requires people to put in a very serious and sustained effort.
Yeah, absolutely. I'm going to squeeze one final question in before we go from David Wood. He says, I guess Professor Russell disagrees with the recent DeepMind publication in which they say reinforcement learning is enough to reach general AI. You've got a minute. Give us your response.
Yeah, so I just read that paper because one of my friends wanted my opinion. And it's not inconsistent. Right, so reinforcement learning and probabilistic programming are not inconsistent at all, right? for particularly model-based reinforcement learning, it will be very natural for it to learn a model in the form of a probabilistic program. But I think that paper, I just find it, let's say it's very similar. The whole basis of the argument is very similar to what we say in the first edition of the textbook back in 1994, that all of the cognitive functions are in the service of rational action. And I think they're really just rewriting those paragraphs in the textbook using the word reward, which is one, reward is one form of defining what constitutes a rational action. So I actually didn't find the paper to say much new, and I think things have gone, our understanding of AI has gone much further than that since 1994, because for several reasons. One is we understand that rational behavior is not possible because of computational constraints, so we have to have a version that takes into account computational limitations. And another really important thing is that we don't know how to specify reward functions. So that causes, the inability to specify reward functions correctly is what causes us to lose control over, human level or superhuman AI systems. So in the book I wrote a couple of years ago called Human Incompatible, I explain all this, and that we actually need a different definition of AI that leads to systems that are provably beneficial to humans. And the reinforcement learning approach will not give us that.
Amazing, Stuart. Thank you so much for that. Thank you for sharing your insights, your expertise, and of course some tasty opinions as well in the Q&A here today. I'm sure the audience have gained so much from the session. It's been really great to get that sort of whistle-stop tour of the tech, as well as a little bit more of that global context. So Stuart, thank you so much for coming and joining us today.
All right. Thanks, Gemma, and thanks to the audience for all your great questions.
I am so sorry for having to cut this discussion short. I think I could have listened for hours. Thank you so much to Gemma and Professor Russell for a detailed and fascinating conversation. I'm optimistic for a future where we can build machines that are capable of understanding, predicting, and making decisions with limited amounts of data. You don't get to say it very often, but I genuinely feel that we've been in the company of a legend. And the audience interest is a testament to that. I have genuinely never seen so many questions.
So many questions. So many questions.
Congratulations again on your massively well-deserved OBE. To everyone in the audience, don't leave the cutting edge stage. Coming up next, we're talking neural networks and computing capacity with Will Summerlin. See you all soon.